Hi guys, today we're going to cover Alkenes Stereoisomers. Now we've been in the alkane chapter, so you might wonder why are we covering alkenes all of a sudden? And the reason why is because we were talking about isomers before. We were talking about how there are conformational isomers of a molecule, so whether it's eclipsed or staggered anti or staggered gauche. Okay, we've talked about different rotations, but it's still the same molecule. Conformers are different conformations of the same molecule. Then we talked about constitutional isomers, and those are molecules that are different from each other in that they have the same chemical formula but different connectivity. So an example would be like straight chain butane or branched butane, which we call isobutane. So here's another example of a kind of isomer that we haven't covered yet. And this is trans-2-butene and cis-2-butene. And you can see how their connectivity looks the same. It's one carbon, then another, then another, then another, and then you have the double bond between carbons 2 and 3. So that looks all the same. But if you build them, you'll see, or if you look at them on paper, you'll see that they're actually different molecules, because here's trans-2-butene. We have a double bond right here, and you've got the two methyl groups on opposite sides of that line. So right here and right here. Now with cis-2-butene, see how the double bond is right here, and I've got my methyl groups on the same side, right here and right there. So if you look at these and you try to convert one into the other, let's take cis-2-butene and I want to make it trans. Okay, it's not going to do that because the double bond is keeping it from rotating. It's not able to rotate around a double bond. So these are what we call stereoisomers. They can't be conformational isomers because you can't have that rotation to convert from one conformation to the other. So later you'll learn these stereoisomers are called diastereomers, or they're called geometric isomers sometimes, or structural isomers sometimes. So later you'll learn that these are called diastereomers in the next chapter, or geometric isomers. And for now, let's use cis and trans. Now, trans is easy to remember. Trans means across. So you have these guys across from each other. And cis, I think of same side. Cis, same side. Another way that we name these is instead of trans, sometimes we use the German entgegen for opposite. So E2-butene is another name for this, and instead of cis we could say Z or zusammen, which means same. Now E and Z, so in this case there's only two groups to compare. So you can use cis or trans in that case. That's called disubstitution. So when you have only two groups, cis or trans is fine. But when you have three groups, then it gets more challenging. So let's review. We have this dotted line going through the double bond. We have opposite sides or across the line from each other, so that's trans or E. We've got the line, these are same side, so cis or Z. And the one way that I remember is E is opposite, so I just say it's epposite, just to try to remember. Z is same side, okay, so that helps me remember which is which. And then this one, notice that there's two groups, they're opposite from each other, but if I switch these groups, it turns out it's actually the same molecule because of symmetry. Remember, this is flat. And let's say that one of these groups was this and the other group was an O and one's an X, okay? So the thing is, if I switch those groups and they were stereoisomers, then this should be different from this. But do you guys see how I could just flip that and it will be the same as this? So whenever you have two groups on the same carbon, they're not going to be cis or trans. I need something over here in order to see if it's cis or trans, okay? Over here we know that this is different from this because there's a hydrogen here, and if I switch those, the hydrogen with the O, you see that the O will be here and the hydrogen will be here, and you'll see that they're actually different. You can't superimpose them. They're different from each other. So this one's more challenging because I don't know which two groups to compare. Do I compare the methyl and the bromine, which are trans, or do I compare the methyl and the ethyl, which are cis? So what I want to do is figure out who to compare. So what I do is use the Kahn-Ingold Prelog rules, which say take a carbon of the double bond and figure out who wins. So we have to see all the ones that are attached. And who wins is based on the first atom attached. So this H is attached to the carbon, and so is this carbon. I'm not comparing the methyl group, I'm comparing the carbon. And I go based on mass. Carbon is heavier than hydrogen, so the carbon wins. So that's one thing that I'm using to compare. Then on this side of the double bond, I have to look at what's attached there. I look at the bromine and I look at the carbon. And bromine is heavier, so bromine wins. And now I compare these two groups. They're opposite or epposite from each other. So this double bond configuration is E. It's sort of like trans, but we can't say trans because these two groups are trans to each other, but these two groups are cis to each other. And so then I don't know which to use in the name. Do I use cis or do I use trans? It just depends on which groups you're talking about. But in the name, I want to use one thing, right? So we just call it E. So let's look at a little bit more complicated case. Let's say we had this molecule. When you have double or triple bonds, then it gets a little bit tricky. So let's say we have something like this. Okay, so just a slight modification of my groups over here. So clearly the methyl group wins over a hydrogen on this side. All right, but then let's look on this side. Okay, is it this group that wins or this group that wins? Notice there's a carbon here. So the first groups that I'm going to compare are the directly bonded groups to this double bonded carbon. So I'm looking at carbon here versus carbon here, and it's a tie. Carbon has the same mass as carbon. And then what you want to do is you want to stay on that carbon but choose the next heaviest atom. Now it's oxygen versus oxygen. They both have an oxygen, so it ties again. Now here's where the pi bonds get tricky. Okay, instead of treating this like a double bonded O, I'm going to treat it as two single bonded O's. All right, so that enables us to give double and triple bonds priority. So let's review. So we first went to these carbons here and they tied, and then we went to the next heaviest on those carbons. So it's sort of like team players. Like if your team, you get to pick the best person on your team to go, and this carbon here chooses its best person on its team to go, and they're the same. Okay, so then it's a tie. So then you go back to the teams and you send your next highest. So here the next highest one is the oxygen, but over here the next highest one is the hydrogen. So that's why this group is going to win overall. So it's this group that wins overall. Based on that analysis. The next heaviest one, okay, go back, the next heaviest one, go back, the next heaviest one. You keep branching out like that until somebody wins, okay? So this is going to be E or Z. So here's our line, and the two top priority groups on each carbon is on opposite sides. So this is also an E isomer. All right, exercise, just assign each of these double bonds as easy or neither. So I'm going to highlight this, and let's do one as an example. This methyl group wins over the hydrogen over here, so this wins. And then over here, neither of these win, right? So there's no stereoisomer. If I switch these two groups, I'm going to get the same exact molecule. So this is called neither. So go ahead and highlight each of these bonds and figure out what's the configuration around each of these bonds, E or Z or neither. All right, guys, so we're back. Here, this is neither because these two are hydrogens. Whenever you have the same groups, you switch it and get the same thing. So this is neither. Hydrogen's over here, so neither. If you need to see it, just draw it in if you need to see it. All right, for this one, let's focus on who's on each one. Carbon versus carbon. So they're both carbon. This one has a hydrogen next. This one has a carbon next. So this group wins. That's for this double bond here. Over here we have a hydrogen and a carbon. This carbon wins. So these two are on the same side of this double bond. So that's called Z, same side. Now let's look at the other double bond, this one. You can clearly see these two carbons are on the same side, hydrogen's on the other. So that's Z as well. For this one, same thing as over here, two hydrogens on the end, so you switch those hydrogens, you have the same thing. For this one, it's not so clear. Okay, you got two methyls here, looks cis, but you have methyl in this group over here. Clearly, this carbon is going to run out of things, so this one's going to win, and then this one wins over the hydrogen, which is over here. So this is opposite E. All right, a lot of students get confused on this stuff, so don't take it for granted. It looks easy. Easy, get it? Bad joke, sorry. But a lot of people have trouble with it at first, so pay attention to it. Give it lots of practice till you really see it. But the point of this is being able to tell that there's different stereoisomers, okay? And by switching groups on the carbon of the double bond, if you get the same thing, then there's no stereoisomer. If you get different things, like cis versus trans, then you're going to have a stereoisomer. All right, good luck, everybody.